Oh, no. Welcome, welcome.
Morning.
How you doing?
All right. Although it's cold and gross in Colorado.
It's cool here as well. Can you co-host? So,
Okay.
welcome
I
everyone.
was just gonna chill and listen, you know.
Yeah, well, if you see somebody pop in that I don't see pop in, you can admit them and stuff like that.
I will do that, and is the chat open for?
Yeah.
Okay, yeah, I'll watch the chat and stuff.
Great, thank you, thank you.
Okay. I'm gonna go get another cup of coffee.
Very good. So we'll get started in a few minutes. If you want to introduce yourself in the chat, you can do that. And I will put a link to the agenda in the chat. And we are live on YouTube, by the way. So if you don't want to be on YouTube, then you can watch the recording later. It is 12 o'clock now, but we are expecting, we have quite a few more registered than who's here so far. So I'm hopeful more will show up. Hi, Christy, good to see you again. So I think we'll wait until maybe 3 minutes after and then just dig in. We've got plenty to talk about, so hopefully we'll have more folks to talk with, but even if we don't, we'll have a good hour and a half. And I am just outside of Buffalo, New York. I telecommute to Ithaca and have been doing that since deep into the before times. I used to be able to say I'm PRI's only telecommuter. That is not the case anymore. Go ahead and share my screen with the agenda for starters. My favorite political cartoon of all time up there. So welcome, we're letting folks filter in. And since we are a small group, I will actually stop sharing and say, let's just introduce ourselves. And so I'm Don Haas. I'm the Director of Teacher Programming at the Paleontological Research Institution, which is in Ithaca, New York, and known in the area by its public venues, which are the Museum of the Earth and the Cayuga Nature Center. And in past lives, I've been a high school science teacher and a professor of education, and have been at PRI since 2008. Alex, you want to introduce yourself?
Hi, I'm Alex Moore. I'm also at the Paleontological Research Institution. My expertise is geological for the most part, although right now I focus on climate change. I have 30 years experience with university students, but have also done a lot of work in the K-12 space and with high school science teachers for the most part. And today I'm supporting Don. He's going to be sharing all this stuff with you.
Yeah, and Alex and I are half of PRI's climate team. Not joining us today are Rob Ross, the Associate Director for Outreach at PRI, and Ingrid Zabel, the Climate Change Education Manager, who are both involved with the whole suite of our programming and resources. And since I know Christy a little, I'm going to point on her to go next, and then she can pick who's next after her. So Christy, you want to introduce yourself?
Of course I do. Hi, everyone. My name is Christy Pratt. I live in upstate Pennsylvania, and I teach high school right over the border at Horseheads High School in New York State. Nice to be here. Welcome, everyone. And I pick Olivia.
Hi, I'm Olivia. I'm a student at Grand Valley State University, and I'm here to observe what you guys are doing.
Grand Valley State is in Grand Rapids, Michigan. Is that right?
Yes.
Yes. Okay. And Ellie, you want to go next?
Yeah, hi, I'm Allie Gillum. I also attend Grand Valley State University, and I'm here to observe as well for a class that we're taking with Professor Callahan.
Great, great. And what, I should have asked Olivia too, what level are you two planning to teach?
I'm doing preschool to 3rd grade.
Awesome. And Ellie?
I plan on going into special education.
Oh, great. Okay, and last but not least, and maybe I'll let you pronounce your name.
Yeah, it's Prabhavati Turaga. Actually, I'm from Houston, Texas. I teach at community college. I teach physics, but I'm interested in global warming and climate change, all this. So just I'm here to know about all those.
Awesome. Thank you. Thank you all for joining us. And I'm hopeful again that more folks will show up, but we'll go with who we've got and be happy with that. So the theme of the next 90 minutes or 84 minutes is talking about the need to replace fire in our energy systems. And you know, fire has been central for humanity, you know, for us to become humans, for us to industrialize society. Fire has been central to the existence of Homo sapiens, and that's worked well for a lot of things for the 300,000 or so years that Homo sapiens have been around. But while it's made modern society possible, and in fact made humans human, it now endangers our very that society that it's made possible. And we need to figure out how to get by with a whole lot less fire, or figure out a way to take out the products of combustion out of the atmosphere. And I should say, I hopefully will say multiple times during the course of the session, that the most important way that we can do that is to simply use less energy. No matter how you generate energy at a large scale, it's bad for the environment. So figuring out ways for things to be more efficient is really central, and efficiency is really only part of the metric. It's not necessarily more efficient to make neighborhoods more bikeable and walkable. It's a kind of a different way of reducing energy demand, but that is really important too. So figuring out however we can stop doing certain things is a really important piece of the puzzle. And as I put in the agenda, what is probably my favorite political cartoon of all time from 1861, and the caption is the grand ball given in honor by the whales in honor of the discovery of oil wells in Pennsylvania. Back at about the time of the Civil War was when we discovered how to get petroleum out of the ground, and that made life better for whales. And but it's got a complicated set of effects. And another sort of important theme, I think, for the day and for thinking about climate change is thinking in systems and thinking how when you change one thing, it may have consequences that you weren't really thinking about, and all of the layers of complex systems. So there is the abstract. We've done the introductions. Now I want you to take a minute and put what you think are put what state you're in. So everybody's in the US here, who's here today, and put where in that. I hate typos. Sorry about that. So put where you're from, so what state you're from, and your best guess on the two largest energy sources in your state for electric power generation. That's a little easier to sort out. So I'll give you a second or two to do that. And I see Alex has put she's mostly in France now. She's in Colorado at the moment. So we've got two Michiganders. I'm using my wait time for folks to put in their guesses, and we've got one Texan.
Yeah, I have no idea what Colorado does for energy, actually.
Yeah, I actually looked the other day and I have forgotten. Oh, and I forgot about Christy because I don't see everybody's name. Yes, Christy's in Pennsylvania. All right, well, let's take a look. And if you scroll down in the agenda, you can see there's the US state energy profiles, and we'll go to that page. I've got it open here. And the Energy Information Administration website is a phenomenal resource for teaching and learning about energy. And another key idea that I'd like you to walk away with today is that you can't, teaching about climate change without teaching about energy is like teaching about lung cancer without teaching about smoking. And that's problematic. So, I am looking at the new site instead of the old site. There we go. So this is actually, there's a beta version they're updating. I am going to the original site, which is the link that's down in the bottom of the agenda. And they've made some changes in the beta version, and I just don't have my head wrapped around that yet. I like some of them, I don't like others of them. And you can go ahead and click on your state. I will, since my colleagues out in Colorado at the moment, we'll take a peek there. And if you scroll down on the page, there's a nice set of quick facts about the state. In the order of 5 bullets, maybe it's 5 bullets for every state, and it just gives you some interesting stuff. Then it's got this 5-tabbed section, and we'll take a look at total energy for starters and see that natural gas is the biggest energy use or biggest energy source in Colorado writ large. And you can see what's after that. Gasoline is number 2, but not by much. Coal is a very close third. And let's see what it looks like for electricity production. And coal is number 1 there. And non-hydro renewables are number 2, and a pretty close second. That is going to be mostly wind and solar, probably mostly wind.
Yeah, I'm curious. I'm really curious about the breakdown of that.
Yeah.
Because
Yeah.
one of the things that you notice, particularly if you fly into the airport in Denver, is that in a place where the sun shines 300 days out of the year, there's no requirement for new construction to have solar panels on the roof. It's really disturbing.
Yeah. Yeah. They, I don't know if they have a requirement about energy use at all, but hopefully they do.
It's very weird. I know Colorado has some very strange rules about energy and about water, that are legacy from the 19th century.
Yeah. Yep. Yeah. And Colorado is actually a pretty big energy producing state. Let's take a look at, we're a small group, so I think we've got time to look at everybody's, if my computer will go fast enough anyway. So we've got a Pennsylvanian. And another one of the key messages that I want you to walk away with today is how incredibly quickly the energy system is changing both in the US and around the world. So again, there's those quick facts. Pennsylvania is the third largest net supplier of local energy to other states after Wyoming and Texas. Our total energy to other states, that is mostly in the natural gas. And that is a huge change from 15 years ago. That's because of fracking, where between, I think, about 2008 and 2013, natural gas production increased by 17-fold. So fracking was a huge rapid change in the energy system in Pennsylvania, probably more than anybody else. So you can see the total energy, natural gas is number one, as in Colorado. There's also an outflow of electricity from Pennsylvania. And when we look at electricity for Pennsylvania, natural gas is by far number one, nuclear is number two, and coal is a pretty distant third. This is for June 2022. That's a big change in the last several years. Coal was certainly number one in Pennsylvania less than 10 years ago, and now it's a pretty distant third. And let's go to Michigan and Texas. So for Texas, natural gas again, all the states we've looked at so far, natural gas has been number one for total energy. And I think natural gas has been number one for electric generation in all the states we've looked at so far. And Texas is actually the biggest wind producer in the country in total number of megawatts. And so most of that non-hydro renewables bar is going to be wind for Texas. And that's a pretty interesting thing that an awful lot of folks don't know. And I think, one of the reasons for looking at this is that most people don't know. And yet a lot of people have pretty strong opinions about how the energy system should change. And I think an important starting place is knowing about where your energy comes from. And so looking at Michigan, again, for total energy, natural gas is number one. Gasoline is number two, which I think was the case for at least Colorado. I don't remember looking at that for Texas. And again, for the third state or fourth state, all of the states we've looked at, natural gas has been number one for both total energy and for electricity. Coal-fired is a pretty close second, with nuclear in third for Michigan. And I'm actually surprised that hydro shows up because Michigan doesn't have that much topography. So it doesn't have that many big hydro plants. I think the highest waterfalls in the lower peninsula of Michigan is 6 feet, if I remember right. A little different from New York State. So this is just kind of a peek at this really wonderful resource of the EIA website, and we'll, I think, look some more in a little bit. I'm also going to do a Zoom poll here. I think I've got set up. If I can remember where to find the polls, there they are. And we'll do this one. So can you see that?
Yeah, we can see it.
Okie dokie. So it's a little bit of a complex question, so take a minute to read through, and I've actually got a slide for it that's a little easier to see than maybe that way. I don't want to give the answer. Why am I on that slide? Yeah, geez, having a hard time here. There we go. Okay, we've got some answers in there. There are your answers, and looking at, get that out of my way, stop sharing. So here are the choices listed in a slightly different way than they are in the poll. And here are the answers. It turns out that all of those answers were right sometime in the last 21 years. For 2020, wind was actually ahead of hydroelectric. It is back above hydro in 2022. So the correct answer for right now is the same as the answer for 2020. Natural gas is the largest producer of electricity in the country, with nuclear in second, coal in third, wind in fourth, and hydro in fifth. And this graph goes up to 2021. And this is also from the EIA website, though I added the animations. And you can see how much change there has been in the last 20 years. And you see solar pop in at the end there, and that is going to be a big deal in fairly short order. In 2021, I think, wind and solar combined passed the 10% of our electricity mark, which is a big deal. 10 years ago, they were essentially nothing, and now they're 10% of our energy picture. So that's a very exciting piece of news, I think, and reason for optimism about where we might end up. And I think, is that the last slide of this set? Yes, it is. And back to the agenda. So we're seeing wind and solar come on the scene, and I want to look at another kind of energy source for replacing a big chunk of our energy picture. And this is looking at the Cornell Deep Geothermal Heat Research Project, where this summer on the edge of campus, they drilled a 2-mile deep hole called CUBO, the Cornell University Borehole Observatory. And that is part of the initiative to move the campus from using natural gas to heat the buildings to using deep geothermal, where if things go as we hope they will go, there will be a few pairs of holes, something on the order of 3 or 4 or 5 pairs of something like 2-mile deep holes, where in one hole of each pair, cold water will be pumped down one hole and hot water pumped back up. We do know from the CUBO that was drilled this summer that it is about 90 degrees Fahrenheit 90 degrees Celsius about 200 degrees Fahrenheit down at the bottom of that hole, which is plenty hot enough. Now we need to figure out if we can make water flow from one hole to another, and have that be economically viable. We'll take a quick look at a video on the webpage. Can you hear that okay?
Transitions from
I forgot to click the button.
The audio
one
was completely
energy
on.
source to another are an be a key to our societies. Heat can be one part of a worldwide transition to heating our buildings without carbon in the energy source.
We have almost infinite energy right below our feet, pretty much everywhere in the world. It's available 24/7 all the time. It doesn't depend on the weather, it doesn't depend on day or night. And if we can just figure out how to use it efficiently, it really solves our energy problems in ways that other renewable sources don't.
Welcome to Going Deep to Solve a Big Problem, exploring geothermal heat. Roberto here and I will be exploring a new project with you over the next few months to understand how we can heat our homes and buildings with water made hot inside the Earth's crust.
Hi, Kiana.
The project is called Cornell University Borehole Observatory, or KUBO. KUBO is a scientific tool to explore an idea.
And I'm not going to show the whole video for the sake of time. And there's, I think, 3 or 4 videos in the series. And in the interest of full disclosure, I'll also admit that that's my daughter. But I wanted to point to that resource in the 90 minutes that we're together. A lot of what we'll do is point to some resources that we won't dig into in too much depth, but make you aware that they're there so that you can explore, and they are linked from the agenda. And now we'll take a look at changing energy. Have I already got this open? I think I do. Yes. Let me look at where we are on time too. I think I'm about right. Assuming that my computer plays along nicely anyway. And we are also a small enough group that you can ask questions anywhere along the line and just speak up. I probably won't be peeking at the chat, but Alex will interrupt if need be. Any questions while this loads? So I will say, while it's loading, the KUBO project began in June, and they drilled on and off for 2 months to reach the 2-mile depth. And it's not actually quite 2 miles. It's I think 9,700 and some feet, if I remember right. Collecting samples along the way. And there will be, we will be adding to that website over the next several months. And one deadline that we have is that a month from now is the New York State Science Teachers Association meeting. And we're doing a workshop there that requires us to have more done on that website than it does right now. So you can look for that. And now we will go into presentation mode here. Full screen. And so humanity, sorry about that. Humanity has always been powered by fire, and sort of the key question for the day is, can we stop that, and do we have to? A pair of questions there. This is a very brief look at energy history. So we start 4.5 billion years ago. It was a mess. I'm glad I wasn't there. Now we're going to look at an absurdly brief history of fuel. So there again, Earth history is 4.5 billion years. And there's the timeline. That's the piece without fire, which I think is an idea that should be understood by a lot more people than, or a fact that should be known by more people than know that now. For 90% of Earth history, there was no life on land, and life is what provides almost all the fuel that we burn. So photosynthesis is at the root of producing plant matter, and it is at the root of how fossil fuels are created as well. Fossil fuels are called fossil fuels for a reason. They're made from ancient life, and all of that stuff was underwater until the Silurian period. And so in order to have fire, you need fuel, heat, fuel, heat, a sustained chemical reaction, and oxygen. And not only was all of the fuel underwater until the Silurian, there also was not enough oxygen in the atmosphere, which we'll say a tiny bit about too. So there's the piece with fire. Let's zoom in on that. There's the first life on land. There's enough oxygen in forests on land. And there's us. Agriculture, civilization, and whatnot is just the last tiny little sliver of that, with the tiniest little sliver of that tiny little sliver being the world since the Industrial Revolution. So the Industrial Revolution, somewhere around 250 years ago or something like that. You compare that to 4.5 billion years, and that's not very much at all. So, you know, one talking point we often hear is that from climate change deniers is that climate has been changing for all of Earth history, and that's true, but climate is changing now because we're burning stuff. And not only were we not around to burn stuff and until 300,000 years ago, and earlier human species have been maybe controlling fire on and off for the last million years or so. But when you compare that to 4.5 billion years ago, that's nothing. And even the natural fires that were occurring before we came along have only been occurring for the last 10% of Earth history. So that's a kind of interesting point. So jumping up to Homo sapiens, we're the only species with dominion over fire. Fire made us human in a lot of different ways. It helped with our digestion to allow our brains to get bigger, and it also made us more social by gathering around the fire. As I said, other early hominids had some control of fire. They're not around anymore. Those earlier hominids got control maybe 1 million years ago, but initially they had control over fire if a fire started, but if it rained a lot and the fire went out, they were out of luck until the next lightning strike or something like that. So Homo sapiens figured out how to start fires, and we've been around now for about 300,000 years. And there are other species on the Earth that use fire but don't control it. And Darwin was among the first to suggest that language and fire are the two most significant achievements of humanity. And that continues to hold up. And there's some resources for going a little further on this if you want to. Now, before the Industrial Revolution, but with humans doing stuff, human power was an important source of energy. And here the diagram labeled those folks as workers. I think that's an interesting choice. They were slaves. They weren't doing that by choice. We've been using animal power, of course, for all pretty much all of human history. We've been using biomass for all of human history. We've been using wind to some degree for a few thousand years in various ways, and water also for a few thousand years. And that's most of our energy sources from before the Industrial Revolution. There are probably some other smaller scale things that folks might be able to think of. The Netherlands, jumping up, getting closer to the Industrial Revolution. The Netherlands became a world power around 1600 through energy dominance, and that's both thermal, heat-based power, and kinetic. So the European forests had largely been cleared by 1600. The Netherlands came up with windmills that were of a fundamentally different scale than any windmills before that, I think. And this video gives a glimpse. We're again going to look at just a couple of bits of the video. It's remarkable that this was technology 400 years ago. I'm actually going to mute it. Figure out where that is. Mute option. Yeah, maybe I won't.
All right, you're in for a real treat. So we've
So
got
I'll just
the
talk over them.
completely on wind power. I
And
just watched a 10-minute video of
what
building this.
a fundamental thing that windmills, these big windmills in Holland in the 1600s
Automated
allowed them to do
air
was cut
with the
very
rope.
large timbers. And that meant
Unity
making
with the
very
wind,
large
so
boats.
the wind gets faster.
So they were able to make much bigger ocean-going vessels than pretty much anybody else. And that gave them a strong military advantage. And this was just one of two sort of key things for the Netherlands to rise as a world power around 1600. The other was peat, which they figured out how to get out of the ground and burn. And that does not look very pleasant. And they became a world power because of that. And eventually their power faded, and it faded in a sort of storyline that plays out over and over and over again throughout Earth history. So you start by figuring out how to exploit an energy source. You master doing that. You use up the easily accessible supplies. So as the Netherlands spread their force, they dug up the peat and used the stuff that was easy to get, and it became more and more difficult, expensive, and environmentally damaging to extract and use what was left. And then it becomes impractical as an energy source. And then somebody figures out the next energy source to do that with. So that happened with peat. It happened with forests in the Americas and in Europe. It happened with coal, and so on, over and over and over again throughout human history. For extracted resources, now we're looking at moving from stuff to take out of the ground and burn to getting to harvesting energy instead of extracting it. And harvesting means that it's replaced by, it's renewable, it comes back. So wind and solar keep on coming to keep us going, so that can break that cycle. For the looking at the Industrial Revolution, of course, coal was central to that. So when the Netherlands were using up the last of their easy to get peat, Great Britain was figuring out how to get coal out of the ground and burn that. And there's a child coal miner, I think, in Pennsylvania, that was converting thermal energy into kinetic energy with the steam engine, and put a steam engine on rails, and you've got trains, and that's one of the first trains. And that is a spinning jenny for processing cotton. And there are the image credits for that. And I will say that this is a powerful photo essay to look at, looking at kids in coal mines. Eesh, what were we doing? And I'm in upstate New York, and upstate New York, as it turns out, is at the center of a lot of interesting energy history. So they're just over the Pennsylvania line, an hour and a half or so south of me, where was the Drake Well in Pennsylvania. And as we noted earlier, that got the whales off the hook to some degree, because whale oil was used for lighting and maybe to some degree for heat. So that was a big change. And this is the city of Buffalo for the Pan American Exhibition in 1901, and all lit up with electric light bulbs by the hydropower plant at Niagara Falls, just a few miles away from Buffalo. And I think it's really interesting to ponder that most human beings had never seen a light bulb. And think about coming in on the train or coming in on your horse and wagon into Buffalo and seeing this after having never seen a light bulb in your life, and suddenly seeing tens of thousands of them. That was a remarkable moment in history. And Buffalo is sometimes called the City of Light because of that. And I've also got a little energy tour map in Google Maps that we might come back to later if we have time for that. Let's look at the stops on it. So there's a Tesla gigafactory in Buffalo, where they are making the solar roof tiles, and that is located here because of the renewable energy from Niagara Falls. So they're able to make renewable energy with renewable energy. Most solar panels now are made with fossil fuels. You have to get very high temperatures and things along those lines. The first commercial gas well in North America was 1825 in Fredonia, New York, just south of Buffalo down here. And the Drake oil well is just over the Pennsylvania border there. And Cornell has been cooling campus since I think about 2005, using lake source cooling, where they draw water from deep in Cayuga Lake and circulate that through campus to cool the buildings, and then return it near the surface of Cayuga Lake after they've extracted the heat from it. And that's been working very well for the cooling side of Cornell's energy needs. And I think there's about 260 some buildings on campus, and they're all cooled with that lake source cooling. And the hope is that we will heat them all with energy from deep geothermal. So there is that. And oops, I didn't mean to exit from the presentation quite yet. And this is our energy picture today, or 2020. And as I noted earlier, 2020 is already a little bit out of date. I suspect this shows a bigger line going from coal than from nuclear. Oh, maybe not. Maybe this is recent enough that. So the thickness of the lines is proportional to the amount of energy for the different energy sources. And so this is the entire US energy consumption, where it all comes from and goes to. Rejected energy use means that's essentially waste heat for almost all of that. It's the energy that was produced but not captured. And you can see that the biggest piece of the pie was industrial, and there's actually some zooming in here. So let me zoom in on some of these. The biggest piece of the pie was industrial, but just barely. I think transportation and industrial uses have kind of bopped back and forth as to which one was the slightly bigger piece in the last few years. In 2020, we actually traveled somewhat less. So industrial, I think, moved into the top spot in 2020 after not being there. you can see that the total, it says up at the top is 92 or something like that. So about a third of our energy is from natural gas and about a third is from petroleum. And most of the petroleum goes to transportation, but some goes to industrial uses, and you can explore around on this graph that's called a Sankey diagram, sometimes more informally called a spaghetti diagram. Buttons work for me. Just fly around there for a minute. And you can, and it's worth noting too that New York is now essentially coal-free. We shut down our last coal-fired power plant in February of last year. And again, I think I've said this once already, but if your knowledge of the energy system is 3 years old, it's out of date. So get up to date. And we've gotten in New York, we've gotten more energy from wind than from coal for probably a decade now. Texas is the largest producer of wind. In the last 12 months, 10% of global vehicle sales have been EVs, and also in the last, and it's actually more than 10% because I put that in there a few months ago. And in the last few months, we crossed the 5% mark for vehicles sold in the US in the last 12 months have been EVs. And I have one myself. And in an awful lot of places today, renewable electricity is much less expensive than fossil fuels or nuclear, especially if you're building from scratch. And I will give a mention to a couple of initiatives at Ithaca and Cornell. Ithaca, the city of Ithaca has pledged to decarbonize, I forget what year the deadline is, 2030 maybe. But what that means is all of the energy use within the city is free of fossil fuels. So they are working to fund the replacement of gas boilers and furnaces and hot water heaters and stoves and dryers and everything in the entire city, so that all of those things are powered by electricity. It's the first city in the country to do that, and it's worth looking into that. And we are hoping to be doing some outreach on this, but we're trying to find the funding for that. And it made the Washington Post and the Onion, amongst other outlets, for that piece of news, and the Cornell Borehole Observatory and the Deep Geothermal Project, as we've mentioned. And that's the end of that piece. And now back to the agenda, and let me, and that's the wrong place. Let me see if there are any questions. I see there's something in the chat.
Oh, that's just me razzing you, Don.
I'll bet Buffalo used that moniker first. Would be my guess. So they've stolen our thunder or something like that.
That picture of the electric lights in Buffalo is extraordinary.
Isn't it? I mean, 1901, when almost no one had ever seen a light bulb. And there they were by the thousands, covering every building on the exhibition grounds. Just remarkable. Okay, next up, I'm slightly behind schedule, but that's okay. We are going to look at where does gasoline go, which Christy has seen before, so apologies to Christy. So there is a chunk of graphite, which I actually have right here. One irritating thing I like. Apple's Keynote for various reasons, but I can't see my cursor in Keynote when I'm in play mode, which is irritating. But anyway, here is that piece of graphite. Graphite is pure carbon. I could not afford a chunk of diamond big enough for the point of this discussion, but that's a chunk of graphite, pure carbon, main ingredient in pencil lead. So if we were in person, I would not pass it around. I want you, and there's a quarter on there to show scale if you don't have me holding it up. And I want you to think about if that is a lot less than the amount of carbon in a gallon of gas, about the same, or if it's a lot more. And I'm just going to plant that seed for right now, and we'll come back to that in a bit. And we've already done this question, so I'm going to skip over that, I think. Yeah, I don't know what happened there. I think I left out a slide or put in a slide I didn't mean to or something. So for the next 20 minutes, I'm going to try to astonish you, scare you a little bit, and give you some hope and motivation to act by telling the story of a gallon of gasoline, which is the source of about a quarter of US emissions are from liquid transportation fuels. Right now in the US, we're burning about 369 million gallons of gas. That's down from before the pandemic. It has not bounced all the way back up. It's bounced some of the way back up, but we're at about 369 million gallons per person per day, which means more than a gallon per person per day, which should make us all say, wow, that's a lot of gasoline. I'm going to throw around some big numbers. So I'm going to have a brief interruption to talk about scale, and there's 0 and a trillion. If we were in person, I'd have you put a sticky note between, I would put sticky notes with 0 and 1 trillion on opposite corners of the front wall of the classroom, and have you come up and put your sticky labeled 1 billion between 0 and a trillion where you think it goes. I think I'm running a little bit behind, so I'm gonna not do this in part also because we're such a small group, but have you do this as a mental exercise. So, you know, point to your screen where you think a billion goes between 0 and 1 trillion, and we'll look at typical answers to that in a moment, but we'll note that everything goes in the first 1/1000th of the length of that line. So if the front wall of your classroom is 30 feet long, that means that your billion sticky should go about a 1/4 inch from your 0 sticky. And people don't get that. And this is responses from an online workshop with a larger crowd than we have today. And you can see that people spread out their answers all over the length of the line. And there are interesting reasons behind that. I think it is true that for the overwhelming majority of human history, up until about the time I was born, almost no one needed to know the difference between a million, a billion, and a trillion. And now I think pretty much everyone does, because in order to meet the responsibilities of, in order to meet civic responsibilities, you need to know this for understanding economic issues as well as understanding environmental issues. And it's not part of our evolutionary programming to understand the differences between really big numbers. So we struggle. One way to help people appreciate it is to talk about time, because we all have some familiarity with a second. And if we add up 1,000 seconds, we get about 17 minutes. And 1,000 times that is a million. So a million seconds is about 12 days. So 17 minutes times 1,000 takes you to about 12 days. A billion seconds is about 32 years. That's a big, big difference. And a trillion seconds then times 1,000 again is 32,000 years. And we have been around, Homo sapiens have been around for less than 10 trillion seconds. Like I said, we've been around for about 300,000 years is the best guess right now. The strategy that I'm using here, and you'll see in a few different ways in the course of the workshop, is called social math. And that's where we think about really big and really small numbers and figure out how to make those things that sound abstract at first blush more concrete by using something that most people understand or are familiar with. So everybody's familiar with seconds, and everybody in the US is familiar with what dollars are. So $1,000, people can picture what that is. $1 million, folks. So, for example, my computer is maybe worth $1,000, or at least when it was newer, it was worth $1,000. And you can probably picture $100,000 house, maybe. Might take it depends on where you live, if you can picture $100,000 house. And $1 million house is something that's now pretty easy to picture in most areas of the country. And thinking about $1,000 million houses brings you up to $1 billion, which is harder to wrap your head around. And one of the things that is kind of shorthand for me is we're now around 330 or 340 million Americans, which means every $1 billion that the government spends on my behalf means $3 of my tax money. So when I hear about $1 billion spending project, I go, well, there goes $3 of my money. Back to the gasoline. As I said earlier, we burn about 369 millions of gas on the average day, more than a gallon per person. And thinking about how to make that concrete, oops, and I've got a leaking, nuts. I have a leaking gallon jug here that was about 3/4 full. Now it's partly on my floor. And I pass this around when we're in person, because gasoline's got a density about 3/4 that of water. And so that gives you a feel for what a gallon of gasoline feels like. I'm going to have to deal with that mess. So if you use 10 gallons of gas a week, you want to think about, that means that 10 gallons weighs 60 pounds. So where does that 60 pounds of gasoline go? Well, in order to figure that out, we first know a little bit of middle school science there, that matter can neither be created nor destroyed, only changed in form. To make sense of it, we need to know what the initial form is. So what is gasoline? Well, it's a complex mixture of hydrocarbons. And a simple definition of hydrocarbons is chemical compounds made out of hydrogen and carbon. And on average, its chemical formula is C8H18. And that is the chemical formula for octane. But it is a mixture, and it varies seasonally and geographically and by legislation. So 10% ethanol in a lot of US gasoline. But C8H18 is about right on average. So what do you get when you burn octane? Well, you get carbon dioxide and water and energy, of course. And looking at that in cartoon form, here is our C8H18 plus 12.5 O2. There's our oxygen diatoms, or oxygen molecules. And here's our octane molecule. And you give it a spark and things recombine. And you end up with 8 CO2 and 9 water molecules. And there are carbon dioxide molecules. There are water molecules. And when we look at those 8 CO2 molecules, they weigh a bunch more than the octane molecule that we started with. And that's not magic, it's chemistry. And there's a little bit more chemistry where we can dig in some more if you want to. So we end up with carbon dioxide that weighs a lot more than the gasoline we started with, because we took oxygen from the air. It's not just the gasoline. So when you burn that 6-pound gallon of gasoline, you end up with 19 pounds of CO2. And that should make you say, wow. That leaves you with another abstraction, 19 pounds of invisible gas. That's kind of hard to wrap your head around. So if we were in person and not COVID-y, I actually did this in person a couple of weeks ago, but opted not to do the balloons because it felt too COVID-y. But I would pass around balloons for everybody. And but since we're not in person, I'll ask you to imagine yourself having a balloon, and knowing, of course, that we're all science teachers here, or future science teachers. We know that an inflated balloon weighs more than an empty one because the gas inside it does weigh something. And the question we want to ponder now is, how many gallons of gas would it take to hold 19 pounds of carbon dioxide? And of course, to figure that out, you need to subtract the weight of the balloon. And I'm going to blow this up to a gallon size in a minute. I'll hold it empty and think about how much it weighs, and you can again do that in your mind. And now we'll blow it up to about a gallon size. Drip, drip, drip. That's about the same size. So now we want to ponder, how many of these would it take to hold 19 pounds of CO2? So in order to process that, it's helpful to think about some things that weigh about 19 pounds, maybe a very large cat or a pretty small dog, 20-pound bag of anything, so 20-pound bag of charcoal or rice or whatever. How many do you think it would take? So you want to stick some guesses in the chat. How many balloons to hold 19 pounds of CO2? And I don't actually expect you to guess right. so don't worry about guessing right. Just take a guess or two. 500, 200, 250. Let's see. It's about 1,100. And you can step through the chemistry depending on what course you're teaching to figure that out. But 1,100 is a lot of balloons. So if we had 12 people here, everybody would have to blow up 92 to get us to that. Here's 100 balloons. And again, this is kind of that idea of social math, of taking something that's pretty abstract and trying to make it concrete. So 200, 300, 400, 500, 600, 700, 800, 900, 1,000, 1,100 gallons of invisible gas from 1 gallon of gasoline. That's a lot of balloons. And you can also, depending on what course you're teaching, you can figure out how many balloons worth of oxygen it took to do that. And I'm sure there are various ways to dig into that more deeply, but the bottom line is burning a 6-pound gallon of gasoline gives you 19 pounds of CO2 with 1,100 times the volume that you started with, because you've made a phase change from liquid to gas. But wow. So if you want to, and we're burning 369 million gallons of gas a day, that's over 7 billion pounds of CO2 produced every day just from burning gasoline. So wow, again. And here we are back to our chunk of graphite. What do you think? Is that a lot less, a lot more, about the same? Here it is again, live in person, or live in virtual. I will go ahead and spill the beans to move us along so we can have some more time for discussion. A gallon of gasoline is about 87% carbon by weight, which means there's 5.5 pounds of carbon in that 6-pound gallon of gasoline. That should make you say, wow, again. So pure graphite's pure carbon. I made a mistake when I ordered it. I meant to order a 6 by 6 by 2 inch block, and I ordered a 2 by 2 by 6 inch block instead. So it really should look like that. We should have 3 times this much carbon is going out your tailpipe every time you burn a gallon of gasoline. That again should make you say, wow. So you may remember that I said I wanted to astonish and scare you as the first parts of this piece of the presentation. I hope you're astonished and scared now, because that's pretty astonishing and pretty scaring. Now, if we want to take it back out of the air, and I'll say again, first off, just don't put it there in the first place. It's much simpler than trying to figure out how to take it back out of the air. It's much easier not to screw something up than to figure out how to fix the thing you've screwed up. But if you do put that carbon into the air, the simplest technological thing that I can think of to get it back out of the air is to plant trees. And it turns out wood is about half carbon by weight. So if you want to grow wood to take that carbon back out of the air, and to make the math simple, we'll say it's 50% carbon. That means you need to grow 11 pounds of wood to sequester each gallon of gasoline that we burn. Wow, again, 369 million times a day, we need to grow 11 pounds of wood. And we can't let that wood burn or decay, or it'll put greenhouse gases back into the atmosphere. And it just so happens that a standard 2x4 weighs about 11 pounds. And I happen to have one right here. So, which I got a new label on. I don't know how well you can read that. But this 2x4 has about the same amount of carbon as a gallon of gasoline. So next time you fill up your tank, watch the gallons tick by and think 2x4, 2x4, 2x4 for each gallon of gas. And that's a lot of 2x4s. So, knock things over. I'll set that down. There we go. And so we need to grow 369 million 2x4s a day. And that's 4 billion pounds of wood every day. And almost 1.5 trillion pounds of wood a year. And we are not doing anything remotely similar to doing that. And that's just a quarter of our emissions. As we're just talking about gasoline, and emissions from liquid transportation fuels are about a quarter of our emissions. So I think we need to think about other ways of dealing with that. And let me actually stop here and see if there are questions or comments before moving on to the next thing. Time, a little behind schedule. That's all right. Any questions, comments? All right, I'll just continue along here a little bit more, and I will have us go into an activity in a few minutes where we actually get to talk besides me. I just wanted to share this graph, which I think is fascinating, and again from the EIA website. And I think it's worth pondering how this graph is relevant to your discipline. And I feel like I've been talking long enough, so I'm going to pause for a minute and actually throw that question to everybody. So how is that graph relevant to your discipline? Thoughts? It's a quiet group.
I'll just, let me turn my camera on too, if I'm gonna talk. I'm gonna just sort of speak to this from a different perspective. As I mentioned in the chat, this past year, I've spent a lot of time living in Europe. And so being able to not have a car has been extraordinarily fun. And it really makes me think all the time about just how nuts it is in the US that we have to drive everywhere. It just doesn't make any sense. And being able to jump on a high-speed train and go any place I want in Europe is just such a joy and such a much more sensible thing to do so that we don't have graphs that look like this.
Right. Yeah. Yeah, and there are a lot of layers here. Any other thoughts?
There's one about you see the COVID spike. Someone in the chat, Christy,
Yes.
said you see the COVID spike there.
Yeah, the COVID spike is stunning. Yeah, so you see, and the graph looks surprisingly like the graph on the back of the teacher-friendly guide to climate change, which Alex and I are co-authors of. And on the back of that is the CO2 graph from Mauna Loa, the Keeling curve. And it's interesting how much these graphs look alike, but but association is not necessarily causation. The spike,
But in this case, it is.
yeah, I mean there is. It's looking at the spikes on it, and if we actually just look at it in an annual graph, then there's a more clear connection. But the seasonal changes that we see in this graph are caused by how our driving changes over the course of the year, and the bottoms are in February. So we're putting out the least CO2 from driving in February of most years.
John,
And,
how come we don't drive in February?
well, it's cold and snowy, and I think people stay home and there aren't big holidays. So December has Christmas, so you drive more around Christmas. And then January, I guess, includes New Year's Eve and getting home from Christmas vacations and stuff like that. And February is also a couple of days shorter than any other month.
We're
But
like
I think
little groundhogs. We just stay buried and wait for
right.
February
Yeah,
to
I
end.
think it's because people are hibernating, essentially. So it's pretty interesting. And then of course, this is April of 2020 right there. Or maybe it's March, I don't remember. But there is you can look at the interactive graph online on the EIA website. And whoop, I lost my cursor again. Come on. It's my cursor. I gotta stop. Yeah. I don't know why my computer does this, but so I can't quite see all of my slide, but we burn 2 million tons of coal a day. That's a lot less than we were burning a few years ago. But it's still a big source of CO2, which should make you say, wow. There's an update of the slide there. And there's a graph coming up here. Here is our graph. Oh, and my cursor reappeared. This, I think, is an encouraging, exciting graph. Our coal consumption is down by a lot more than half. We were well over 1 million, 1,000 short tons of coal in 2007 and 2008. And in 2020, we dipped below 500,000. And that's really a phenomenal, exciting change. And it's multi-causal behind it. So I'm not going to look at those other slides because they're out of date. I'll pause I'll actually stop screen sharing for at least a minute to see if there are questions, comments, what have you. I'm disappointed there are only 4 of you, I'll confess. There were 19 registered. Where is everybody? But we will slip into how many fires burn for you. And there's a link in the agenda, which I will copy and put in the chat. There. And let's see. So we're going to spend just a few minutes looking at this, and it's basically digging into that question of how many fires burn for you. I think that there are billions of fires burning on planet Earth right now. Most of them controlled fires, and I'm counting the fires in internal combustion engine as each one of those is a fire. So when your car is driving around, it's really a series of sparks and explosions, but we'll call that a fire for the sake of this exercise. And for everything that's being transported to you or away from you, there's some vehicle doing that that's burning fuel. So, and this is labeled as an unfinished exercise, and I welcome your feedback on it. I will go back to screen sharing. For a minute here. So, what I want us to think about is trying to figure out how to wrap our heads around how many fires there are that are burning because of us, each individual. So how many fires are burning for Don? How many fires are burning for Alex, and so on. I didn't write this today, so my furnace I have not actually turned on yet, though it's been cool. It will probably happen sometime this week. For the first time this year, I will turn on my furnace. So thinking about where your electric power comes from is also part of the figuring. But I think I'm going to try and shut my mouth, and I'll actually take my leaking water jug away for a minute and get a glass of water, and I will be back in 2 minutes while you think about how many fires are burning for you today. So back in a minute. Think about that.
It's an interesting question, because normally when we ask questions like that, we think about what it is we do ourselves, home heating or our own car, and don't often think as hard about, the goods and services that we take advantage of. And that's a much harder thing to get your head wrapped around.
I will note too that I've been thinking about this question for a long time, and I don't have any real confidence in my own answer. But I did put my own answer down lower in the agenda, or in the document rather. So what do you think? I'm going to stop screen sharing. Encourage people to speak. You want to take a stab at how many fires are burning for you?
Yeah, actually, after looking at this document, I can realize that it's a hot water heater, and a lot of time we will be on internet, and in winters we turn on heaters, we drive cars. Yeah, a lot of CO2 we are also releasing into the atmosphere. Yeah, it's really fascinating to learn about this.
Yeah, and I'll note too that you're sitting in Houston, Texas, which is maybe the energy capital of the,
yes,
the U.S.
Oil and gas industry, yes.
Yeah, and I'm in New York State, so I'm in the state with, I think, the second lowest per capita energy use in the U.S., and you're in the state with the highest.
Highest.
But it's a little unfair for either of us to lump us into the state, because the reason that New York has the lowest energy use per capita is because of New York City and people living in very densely packed with good public transit. So that's not me. I do not live in New York City, so I don't get the advantage of that. Though it's interesting too that upstate New York, and another resource that I just learned about from our colleague Ingrid Zabel yesterday is if we go back to the agenda, to the agenda and scroll down to the resources, the EPA's Power Profiler is really cool, which I've got open. Let's see if I got it open to the homepage for it. So this compares energy use around the country, and it's not on the homepage. I'm comparing New York upstate to the nation. So upstate New York, we get gas is 26% of our fuel mix for energy production. Nuclear is 31%, hydro is 34.5%, which means that between hydro and nuclear is 67%, and then another 5% from wind. The overwhelming majority of my electricity is low carbon or zero carbon. And you can, so let's look at Texas. Texas, and again, this is for electricity, and it's a little bit more than Texas. I forget what, oh, no, Texas is its own grid. So it pretty much is just Texas. For the rest of the country, it's crosses state borders for many of the regions shown here. But for Texas, it's 50% natural gas, 16.5% coal, nuclear for 10%, and wind for 20%. And so you can see, you can click around on the different regions. So Pennsylvania, where Christy is not too different from the national picture, although a bigger slice of nuclear than and a smaller slice of wind than the national picture, and smaller slice of hydro too. And for our Michiganders, which it fails to, which it's not just Michigan, but you're in the lower peninsula of Michigan. So these aren't quite state lines, but Michigan is actually pretty close to what the national picture looks like. And let's see if I can go back to the.
I'll point out while you're clicking around on that the average European uses half the amount of energy of the average American.
And then electricity from wind and from hydro, that's a new development in the last couple of years. And the fact that coal has fallen to number 3 is also a new development. in the last couple of years. It's remarkable how quickly the energy system is changing, and most people don't have a clue about that, and I think they should. So I'm hoping you'll walk away with that lesson as one of the ones to pass along. So we got 7 minutes left, and I'm going to stop sharing and open it up for questions and comments again. Thoughts, smart remarks. Do you like my new labeling on my 2x4? Just did this. Just made it pretty.
Oh, cool. Very cool.
Yeah. I have found the 2x4 to be very well received. So for our future elementary and pre-K teachers, do you have questions about how or thoughts, ideas to share on how you might bring this to the wee ones?
I think that the example you used with the piece of wood, like all of the big numbers and like seeing how like it sounds like a lot, but when you break it down, it's actually a lot more than you think. So I thought that that was cool how you had that and used that as an example, which I feel like is something that could be used in the future in a classroom.
Yeah. Yeah, and I think probably for the little ones, thinking about just how to use less energy is a understandable idea at every level, that because using energy is wasteful, we should figure out how to use less energy. And it'll also maybe have the advantage of costing less and maybe getting us in better shape if we're walking to school instead of biking or instead of taking the bus or getting a ride from somebody in individual car, which has increased a lot because of the pandemic, is people not wanting to get on buses. So more and more kids being driven to school, which I would like them to ride their bikes or walk.
Yeah.
I think too, and I think, oh, sorry, go ahead.
Sorry, I was going to say that I really liked the balloon example. I feel like it would be kind of hard to illustrate in a class of like younger kids, but I also feel like just like explaining it kind of how you did, but like dumbed down a little bit, would be able to get the point across to younger kids.
Yeah. Well, I think they can understand that, stuff doesn't just really disappear. It changes into something else, and you can make some sense of that, and you can demonstrate that easily. Just, you get a flask that you can put a balloon over the top of, and even just put that in the window, in a sunny window, and the balloon will stand up when the sun is shining on the bottle, especially if you put a little bit of water in the bottom of it. So a balloon will stand up on the neck of a bottle when it's hot, and fall down when it's cold, and you can stick it into a hot water bath or a cold water bath to make that happen faster and stuff like that, so that you can see that there is something there. And of course you can fan kids to make them feel the force of the air, and interesting demonstrations about sticking a meter stick or a cheaper piece of wood under a newspaper and slamming and having it stick off the end of the table, and you slam down on the end of the stick and it breaks because of the air pressure holding down the newspaper. So there are ways to show kids that there's stuff that they can't see.
I was going to say with younger kids, one of the things to think about is what we eat, because I think that's something that they can, obviously they interact with that every day. And it's a less direct line to think about the carbon emissions associated with food than, for example, burning gas in your vehicle or to heat your home. But it actually turns out to be a really significant element of each of our individual carbon footprint. And it's also a really nice one to think about because of all of those things. It's one of the elements of our carbon emission that each individual has a whole lot of control over. And when we talk about not only ease of change, but cost of change, it costs so much less not to eat meat. And so, you know, when we worry about what the economic impacts are of changing various aspects of, you know, what the sort of global or national lifestyle that we live, that one is that's the low-hanging fruit, is changing how we eat.
Yeah, and you know, and also in addition, I'm a vegetarian of 30 years standing, and largely for environmental reasons. But another piece of the food system question that's easy for everyone to understand is that we waste about 40% of the food that we grow in this country. And if we can figure out how to not waste so much, you know, every step of the process of making, packaging, shipping food takes energy and produces emissions. And so if we can figure out how to take that 40% number down to 10% or something, that's a huge difference. And I'll also say, while I'm talking about these personal changes are not enough. The most important thing that we can do right now about climate change is talk about it. So getting our students to talk to their families and their community is hugely important. Individual changes are important though too, because it helps to both build understanding and behaviors can be contagious. So if we can get people to engage in you know, wasting less food or being vegetarian or, you know, eating less meat, or just, you know, generally wasting less, then that spreads. And, you know, it also, you know, there's been studies showing that solar panels are contagious. And my neighbors, I don't have them because, you know, if I turn my camera around, you can see I've got some pretty big trees in my south facing window. But this house over here, the one with the porta potty out front, they've got solar panels on the back of their house, and they were one of the first in the neighborhood. But now there are at least, I think, 6 or 8 houses in the 2-block area that is kind of, my neighborhood is a loop, and there are at least 6 sets of solar panels in the 2-block loop here. And so those individual changes can be contagious, but you got to talk about it. That's a really, really important idea. And kids can be powerful influencers. There was a study of 2 or 3 years ago that showed that daughters are particularly effective at helping their dads and granddads understand stuff about climate change. So, and we are slightly over time, but I'm glad to stick around if there are questions or comments or whatever. And thank you for joining us today.
Thank you so much. It's really eye-opening and fascinating webinar. Thank you so much.
Thank you. And the agenda will stay there, and I will add a link to the video from today as well. So thank you all.
Thank you.
You.
Are we?
Good one.